Yeah, you can start entering your attendance. Yeah. All right. So yesterday, what we did was we took the H modeling, right? We proposed equivalent circuit, and we also derived, what do you say, this equivalent hybrid model, right? So we started with exact hybrid model, and then we also considered approximate hybrid model, right? So today, what I will do is, in the first half, let me carry out analysis based on hybrid model, okay? And in the second half, let me talk about uh, something known as Darlington emitter follower. It is your conventional emitter follower, only the difference is that your Darlington emitter follower will have two transistors connected in a definite manner. All right, fine. So let's consider the analysis. Okay, so analysis. Using H model. Okay, what I will do for the analysis sake, I'll consider only one circuit. Okay, whatever steps we follow in this particular circuit can also be used for any other circuit. Okay, so to begin with, what I will do, I'll consider voltage divider amplifier. Okay, in short, voltage divider bias AC amplifier analysis. Okay, all right. So first, let us draw the circuit diagram of voltage divider bias AC amplifier. Okay, and this is your RC, R1. Okay, so it's the bypass capacitor, which provides low resistance path for the AC signals. Okay, followed by the two coupling capacitors. One is found in the input circuit, and the other is found in the output circuit. This is Vi, and this is V0. Okay, fine. So this is your voltage divider bias AC amplifier. Okay, now we need to go for hybrid model analysis. You see, the obtaining the equivalent circuit doesn't change much from your RE model, right? So in order to get an equivalent circuit which fits for AC analysis, what we have to do is, as discussed in the RE model, you need to ground the VCC and then replace capacitors with short circuit equivalents. Okay, so the same steps holds good for even your hybrid model analysis also. Only the difference is that in place of RE model, you're going to place the approximate H model. So what I will do is, I will write this statement: replace transistor symbol with approximate H model. That's all you have to do. Replace transistor symbol with approximate H model. So what I will do, the transistor, let me take it in the blue color. Okay, so over here, first let me draw the H model of the transistor, the base. Okay, so in H model, on the input side, we have HI. Since it is in common emitter configuration, it becomes HIE. All right. Similarly, on the output side, you have a control source, right? So the description of control source going to be HF E IB, where IB is the input current. All right, so that's your collector terminal. Okay, fine. And this is your emitter terminal. Let me keep it as it is. Let's see what to do with the emitter terminal later. Okay, so that's my transistor H model. Right, now what I have to do is I have to connect the remaining circuit elements. Okay, so if you observe carefully, R1 and R2, they are connected to the base terminal, right? And the free end of R1, I mean the opposite end of R1 is connected to VCC, but I have already told you VCC will be grounded for AC analysis. So two ends of, each end of R1 and R2 gets connected to the base terminal. So let's connect. So this is your, say, R2, and this is your, say, R1. Okay, so it's connected to base, and the remaining terminal is connected to ground. Okay, fine. And on the output side, okay, this is your base, collector, and emitter. To the collector terminal, you have RC. Okay, and the other end of RC is connected to VCC, but VCC is maintained at ground potential for AC analysis. Okay, what happens to emitter terminal? Now, emitter terminal, okay, will be at ground potential. That's because when you short circuit when you replace capacitor with the short circuit equivalent, what happens is that it short circuits resistor RE. Hence, your emitter will also be at ground potential. Okay, so that's your hybrid model. Okay, so it is actually, it resembles your RE model itself. Only the difference is that parameters we have changed. Okay, that's your V naught. Okay, we'll mark the two-port, convention currents, input current II, output current I naught. Okay, yeah, that's all. And yeah, of course, if you want to keep, you can also keep the admittance. Okay, normally this admittance is very low. Okay, all right. So for, I'll just write 1 over HV. Now comes the analysis part. Okay, so let's start with input impedance Zi. Okay, by now I think you guys are very familiar with how to extract input impedance, output impedance, etc., etc. Right? So input impedance Zi, if you look at, okay, on the input side you have base node and the ground node. Okay, of course you have emitter node, which is common to input circuit as well as output circuit, but emitter terminal is already at ground potential. So what you have to do is you have to collect the resistors which are coming across base and ground terminal. Which are those resistors? R1 parallel with R2 parallel with HI. So that's your input impedance. Okay, I'll tell you the similarity. If emitter bias is considered, okay, so this is for voltage divider bias. If at all you have had an emitter bias circuit, you would have had RB parallel with HI. Okay, so okay, yeah, so Zi would have been RB parallel with HI. So that's your first performance parameter. Okay, the second performance parameter, let's go for Z naught. Okay, so what do you see when you look at the network from the output side? So output side, we have terminal C and terminal E. So terminal E it is at ground potential. So across collector and ground, we see that RC and 1 over HOE are connected in parallel. So Z naught is basically RC parallel with 1 over HOE. Okay, let me write this. HOE is nothing but output admittance. Okay, it is output admittance. Okay, so that's your Z naught. If 1 over HOE is very large, okay, if 1 over HOE is very large, then your Z naught, approximately becomes RC itself. Okay. What I want you to do is I want you to compare these results with RE model. Okay, you will find that similar terminologies. Okay, against HIE in RE model, you may have beta RE. That's all. Okay, and against 1 over HOE, you may have R naught in your RE model. Okay, so third one is voltage gain. Only you have to replace the transistor parameters. Okay, everywhere you have to write H parameters. All right, so voltage gain by definition is the ratio of output voltage to input voltage, and output voltage is I naught into RC parallel with 1 over HOE. Okay, and also your I naught is basically IC. Okay, I naught is basically IC. Okay, because current through 1 over HOE is negligibly small, so you can write, approximately I naught is equal to IC. Okay, so you can write V naught is equal to minus IC. IC is what? HFE IB into RC parallel with 1 over HOE. Okay, that's your I naught. And VI. Okay, so VI, we can write it as IB into HIE. I hope you understood. IB into HIE. Let me draw the equivalent circuit because I don't want to take II current because I will not have any ratio between II and IB. That's the reason. Okay, so this is my HIE. Okay, this is my VI, and we know that through HIE current IB flows. So on that basis, I have taken VI is equal to current into resistance. Okay, so therefore the voltage gain AB becomes minus HFE because V naught, right? Against V naught, I have this expression minus HFE into IB into RC parallel with 1 over HOE divided by VI. VI is what? IB into HIE. So what happens is that IB gets cancelled. So you're left with voltage gain AB as negative HFE into RC parallel with 1 over HOE divided by HIE. Okay, so that's my voltage gain expression. Okay, and finally you have the current gain expression. Okay, current gain expression. So in the current gain expression, you can write AI is equal to I naught by II. Okay, but we know that I naught is equal to negative V naught divided by Z naught. Z naught. Okay, and similarly, II is equal to VI by, let's say, Zi. You have ready-made equation for Zi, right? In step number 2, you have calculated an expression for Zi. So you have to just take out the ratio. So minus V naught by Z naught into Zi by Vi. So we have this, ratio V naught by Vi, which is EAV. Okay. See, it is minus V naught by Vi. So V naught by Vi is here. So minus of minus becomes plus into Zi by Z naught. Okay. If you want, you can just substitute. Okay, Zi and Z naught expression. Okay. So it is AV. Okay. Into Zi, right? So what is Zi? Zi is R1 parallel with R2 parallel with HIV divided by Z naught. Z naught is just now we calculated, right? It is RC parallel with the 1 over HOE. So that's your current gain. So this is how we calculate the performance parameters of any AC amplifier using H model analysis. Okay, is it clear? Is it clear?
Yes, sir.
Okay. So it's a very simple case, okay, because I considered bypass capacitor, right? So this is with bypass capacitor. So what I will write, bypass capacitor. Now what I'll do, I'll consider the second circuit, which is slightly complex than the previous circuit. So yes, unbypassed capacitor. So I'll write voltage divider bias amplifier with unbypassed capacitor. Okay, so all right, unbypassed capacitor. So okay, anyhow, I have considered voltage divider. Now what I will do, let me consider emitter bias. Emitter bias, just to give different perspective. Yeah, so this is my emitter bias circuit, right? This is IC, this is IB, and this is IB. As you can clearly observe that emitter terminal is not having any capacitor. Okay, so it is an unbypassed capacitor case. Yes, so we will take up the H modeling. Okay, so first let us replace the transistor symbol with hybrid equivalent model. So this is my base terminal. This is HID because I'm considering common emitter configuration. This becomes HFE IB, where IB is the current through HIE. Okay. And this is my emitter terminal. Okay, and on the output side, I have my collector terminal. So collector terminal will be connected to RC. And on the input side, I have RB. RB. Okay, and then I have my VI with respect to ground. Similarly, I'll have my V naught measured with respect to ground. Let me put the polarities. Okay, so this is my II and this is my I naught. Okay, now emitter is not at ground potential because there is a resistor RE. Okay, so what you have to do is you have to draw the emitter resistor as well. Okay, and then you draw the ground connection. All right. And through the emitter, current IE flows. So what I will do, current IE is nothing but 1 plus HFE times IB. Okay, remember one thing, beta in RE model, right? Beta terminology, we use it in RE model, and the analogous terminology in H model going to be HFE. So this is in H model. So what I've done, your emitter current IE is 1 plus beta times IB. So in place of beta, I have substituted HFE. So IE is equal to 1 plus HFE times IB. That's all. Rest all remains the same. Okay. And you can start extracting ZI, Z0. Everything remains the same. It is just like your RE model, except for the terminology. So this is ZI, this is Z0. Okay. So ZI is basically VI by II. Okay, but things are not straightforward here because between base and ground, okay, you have RB in parallel with these two resistors, right? HIE and capital RE. The only difference is that you cannot consider HIE and RE in series connection, provided you circulate the same current through these two, right? Because through HIE, in as it is condition, current IB flows, and through capital RE, the emitter current IE flows. So that's the reason what we are trying to do over here is that replacing emitter current IE with some equivalent, base current. So it is some gain times the base current, the emitter current, right? So that's what we have done. So what we will do is that we will measure the input voltage VI across the base terminal and the ground terminal. Okay. I've just shifted the input measurement. Okay, so input voltage measurement. I've just shifted towards the H parameter model. Okay, so what I can write is that I can write VI is equal to, okay, that is base to ground voltage is equal to voltage drop across HIE plus voltage drop across capital RE. So that's IB into HIE plus IE into RE, or IB into HIE plus 1 plus HFE into IB into RE. Or you take out the ratio VI by IB. Let's define this ratio as some impedance ZB, the base impedance ZB. And base impedance ZB going to be HIE plus 1 plus HFE into RE. Okay, so that's your base impedance. Once base impedance ZB is found, you can find ZI. So now ZI going to be RB parallel with ZB, right? It is similar to your RE model. Just that in ZB description, you have H parameters. All right, so that's your output impedance, input impedance. Next up, we have output impedance Z0. Okay, so output impedance Z0, you can actually try out to find out output impedance Z0. What you will do is you will, try to open circuit the current source. Okay, when you open circuit this current source, current through RE becomes 0, because when IC is 0, your approximately you can say IE is also 0. Okay, so due to which your Z0 comes RC. Okay, so Z0 you can write it as RC. You can write down that actually. Okay, for detailed steps you can roll back to RE model. Okay, next you have voltage gain AV, which is V0 by VI. That is minus I0 into RC. Okay, because V0 is I0 into RC, and VI is IB into say ZB. Okay, and you can also write I0 is IC, right? So I0 is IC, so IC is minus HFE into IB. into RC divided by IB into ZB, right? What is ZB? Somewhere over here we have ZB is HIE plus 1 plus HFE into RE. So IB gets cancelled. We will be left with AV is equal to minus HFE RC. Okay. And in the denominator, I have RE. Okay. Into HIE. What I will do, 1 plus HFE, let me write approximately HFE itself. So plus HFE. Okay. Plus HFE. Or you can write AV is equal to minus HFE RC divided by, so this is actually RE into HIE plus, I'm opening the bracket, RE into HFE. Okay. In approximation, okay, in approximation. No, I mean, you can just keep this as your expression, okay? This is your exact expression. Let me clear it off. This is your exact expression, okay? I'm just trying to show you the approximate expression, okay? In approximation, what we can do is the product, RE into HFE, okay? If RE into HFE is way bigger than RE into HIE, okay? You can approximately write AV as minus HFE RC divided by, so RE into HIE is smaller compared to RE into HFE. So you can write approximately RE into HFE. So HFE gets cancelled. So an approximate expression, crude expression for voltage gain going to be the resistance ratio RC by RE. Okay, RC by RE. So that's your voltage gain. And finally, you have your current gain. Current gain is very easy to calculate. I naught by II, which is equal to minus V naught by, say, Z naught into ZI divided by VI. Okay. So that's your voltage gain AV. So current gain AI is AV times ratio of input impedance to output impedance. Okay. Input impedance to output impedance. So that's your H parameter analysis. Okay. Now, I have done the analysis of two circuits. So homework going to be fixed bias amplifier. Okay. Next, voltage divider bias amplifier without CE. First, second, and third one going to be collector to base bias or collector feedback bias, and fourth one going to be emitter follower. Emitter follower. Okay, so all these circuits I have solved in RE model. Now in H model, I have done only two because the analysis remains the same, and I'm going to leave these four circuits for you guys. Okay, so this you have to submit me as assignment after your second internals. Anyhow, I will float these questions in Google Classroom. Okay, this you need to submit as assignment in Google Classroom, not now, after your second internals. Okay, fine. So that's the end of H parameter analysis. Okay, now there are other aspects of H parameter model that I will take it up after your internals. Okay, so now what I will do, I will consider something known as a very special emitter follower circuit, okay, which is called as Darlington emitter follower. Okay, actually it comes in module 3. Okay, but since I'm discussing emitter follower in module 2, so I don't want to keep this stuff in module 3. I want to discuss this Darlington emitter follower in module 2 itself. Okay, because there is some mismatch in the content in the curriculum. Okay, all right. So Darlington emitter follower. Okay, in short, it is called as super beta transistor. Okay, as the name suggests, super beta means the beta value is very high, very high. So a single transistor gives beta or HFE normally in the range of hundreds to 200, right? So in order to get, a current gain more than 200 or more than 300, what we have to do? So what we have to do is we need to go for a Darlington emitter follower. So this Darlington emitter follower is basically consisting of two transistors. Okay, a pair of transistors are connected in a definite manner so that you would get the overall gain beta as the product of two current gains. Okay, example, if let's say beta 1 is equal to beta 2 is equal to say 100, HFE value is 100, then imagine the value of beta d. So it is 100 into 100, just imagine. Okay, it is about 10,000. So that is the power of the Darlington transistor. It gives extremely high current gain. Okay, so this extremely high current gain is required whenever the load current is quite high. Okay, you have seen in transistor circuits is that your collector current normally lies in the range of millis of amperes. What if your load requirement is in the range of few amps, few amperes, say zero 0.5 amperes, zero 0.1 amperes? So you have to go for a transistor which can handle larger current values. So for that sake, you can go for Darlington emitter follower. So Darlington emitter follower features are large current gain. Okay, let me write features: large current gain and voltage gain. It is approximately equal to 1, just like any other emitter follower circuit, and good impedance matching. Good impedance matching. Okay, so that means to say Zi is high and Z0 is low as expected. That is what an emitter follower circuit should be doing it. So that's what it does. Okay, only the exception or only the addition is that it gives extremely high current gain compared to conventional emitter follower circuit. Okay, all right. So let's see how exactly it gives very high current gain. Okay, so if you look at the internal circuit of Darlington emitter follower, it looks something like this. Okay, so emitter terminal of first stage is connected to base of the second stage. Okay, and the two collectors are connected together. Okay, and this is your base terminal. So what I'll do, I will not write VCC. Let me just take this as collector terminal, and this is your emitter terminal. Okay, so the internal, if you purchase a Darlington emitter follower or Darlington transistor, okay, this is called as Darlington transistor. Darlington transistor. Okay, just like a normal transistor, it will also be having 3 terminals. But what you have to understand is that within the transistor, okay, within the package, there are 2 transistors, say Q1 and say Q2. Okay, so the equivalent, symbol for Darlington transistor can be given just like this. Okay, just like any other 3-terminal transistor device. This is base, This is collector and this is emitter. So let's represent the Darlington gain as beta D. Okay. So what is beta D? Is beta 1 into beta 2. Okay. How exactly it comes? Let me show you. So this is your first transistor. So what we will do, we will take the first collector current as C1. Okay. Let me write. This is C1. This is C2. This is E1. Okay. This is B1. Okay. So this is E2 and this is B2. I've just written different terminals there. That's all I have done. So this is IC1, IB1, IE1, IB2, IE2, IC2. Different current directions. Okay. Next, let us define beta D. What is beta D? Beta D is nothing but output current to input current, right? The current gain expression is always output current to input current. But with respect to our transistor, output current is your second transistor collector current. So that is IC2 divided by the input current. Input current is your first transistor current. That is IB1. So it is basically IC2 divided by IB1. Okay. Now let us also mark the current gains. So for the first transistor, let's take beta 1 as the current gain. And for the second transistor, let's take beta 2 as the current gain. Now IC2. Okay, what is IC? In general, IC is beta into IB, correct? So with respect to IC2, it is beta 2 into IB2 divided by IB1. Okay. Or beta D is equal to, okay, beta 2, let me write as it is, okay, into IB2. Okay. Now, can I write IB2 as IE1? So IB2 is equal to IE1. Wait, let me just write IE1 divided by IB1. So inside, let me write. If you see, the first transistor emitter current, okay, will get into the second transistor base terminal. So IE1 is equal to IB2. So IE1 is equal to IB2. Okay. And IE1 approximately can be written as IC1, right? So you can write beta D is equal to beta 2 into IE1. So approximately IE can be written as IC. So it is IC1 divided by IB1. Now what is this ratio IC by IB? IC by IB is beta. So this is beta 1. So therefore, transistor or the Darlington current gain beta D is equal to beta 2 into beta 1. So that's the proof. Okay. So if beta 1 is equal to beta 2, then your Darlington gain will be beta into beta, which is equal to beta square. Okay. Since current gain is increasing by a large margin, that's the reason it is called as super beta transistor. Super beta transistor. Okay. So that being said, you can take up the Darlington emitter follower. Okay. So what I will do, okay, I'm left with 5 minutes here. Let me quickly draw DC bias Darlington. Okay, DC bias Darlington circuit. Okay, DC bias in the sense there will be no capacitors connected. Okay, so first let me quickly draw the Darlington configuration. Okay, so emitter of first transistor is connected to base of the second transistor, and the two collectors are connected together, and these two collectors are connected to power supply voltage VCC. Okay. Let us connect these collectors together. Okay. And that point, let us connect it to VCC. One and the same, okay, because I wanted to show you the biasing resistor connection also. That's the reason. Okay. So this you can connect it to your power supply voltage. So this is your RB. And on the second transistor side, you will have emitter resistor RE. Okay, so this is your Q2, this is your Q1. Remember one thing, RC is 0 for emitter follower circuit. You can go back and you can cross verify. Okay, RC is always 0 for emitter follower circuit, because if you keep RC, then there will be amplification. We don't want amplification. Instead, we want impedance matching. Okay, that's the reason. You have to be very careful. If you place RC, you will not get even a single marks in exam. So you're not supposed to place RC. RC should be treated as short circuit or 0. Okay, fine. Now let me mark the current directions. Base current IB. Okay. Collector current IC. So this collector current IC split into two halves, IC1 and IC2. And in the end, you have IE. Okay, fine. Apply KVL to base emitter loop. Okay, apply KVL to base emitter loop. So what do you get? Okay, what you have to observe here is that this is base and this is emitter, right? And once again, you have the base terminal of second transistor, and you also have the emitter terminal of second transistor. So there will be two base to emitter voltages. So this is VBE of first transistor. Similarly, you have VBE of second transistor, plus minus, plus minus. So VBE of first transistor and VBE of second transistor. So when you apply KVL on the base emitter loop, that is in the left bound region, you would get VCC minus IB into RB minus VBE and the second VBE, and then it comes the drop across the emitter resistor is equal to 0. Okay, or you can also substitute IE is equal to 1 plus beta D times RE into IB, okay, because beta D is the overall gain of the transistor. Okay, so against IE, we have 1 plus beta D. So therefore, VCC minus IBRB, okay, minus 2 VBE minus 1 plus beta D times IB into RE is equal to 0. Or the base current IB is basically VCC minus 2 VBE, okay, divided by RB plus 1 plus beta D times RA. Okay, so it is actually similar to your conventional emitter follower expression, right? The same expression you are going to get. The only difference is that you have super beta gain beta D and you have 2 VBEs. Okay, so 2 VBEs is due to the presence of 2 transistors. So once IB is found, you can find IC as beta D times IB, right? Yeah, so that's your Darlington emitter follower circuit. Okay, so you will get case study from the which one? I mean, other day I have sent, right? Based on the presence of RS and RL, how the source resistance RS and load resistance RL is going to affect the AC amplifier performance. So that will be your case study question. And innovative question going to be a problem based on Darlington emitter follower circuit. Okay, Darlington emitter follower circuit. So what you have to do, you have to read the analysis of Darlington emitter follower. Okay, so material I will provide right after this class. Okay, I hope you have punched your attendance. Okay. Okay, I'll stop the recording.